Hello friends, good morning all of you. Here I am Gadekar Sachin Pandit. Today we are discuss new chapter such as PMR spectroscopy. Okay, so in this chapter we are discuss first introduction of PR spectroscopy, then basic principle of PMR spectroscopy, magnetic nuclei and non-magnetic nuclei, then nuclear excitation, generation of energy levels in PMR spectroscopy. Okay, so first of all, last lecture yesterday we are discuss IR spectroscopy. Okay, so in this lecture, last lecture yesterday, we are discuss application of IR spectroscopy for structure determination. So in which last lecture discuss a application of IR spectroscopy for structure determination. So first we discuss a different regions are present in IR spectroscopy. So first is the functional group region. So in this functional group region occurs a functional group. Frequency absorbed near about 4000 to 1300 centimeter inverse. Okay. So next is the fingerprint region. So in this fingerprint region we are used as a it helps fingerprint region helps to the detect the similarity of molecules. Okay, if molecules have identical IR spectra in this region means fingerprint region, and if they have the two components must have be no one or same structure, not different. Okay, so that's why we use a fingerprint region. Okay, so fingerprint region absorb frequency near about 1300 to 909 centimeter inverse. Then next is the aromatic region. Aromatic region start from 909 centimeter inverse to 625 centimeter. Okay, so in this aromatic region, this region helps to know the substituent present in aromatic compound. Okay, substitution pattern in the molecules of aromatic compound. Okay, so next we are discuss a structure determination in which IR spectroscopy study the progress of chemical reaction. That's why we use a IR spectroscopy. In the IR spectroscopy, we helps to study the progress of chemical reaction. Okay, similarly hydrogen bonding, detection of hydrogen bonding, that's why we use a IR spectroscopy, helps to the IR spectroscopy to detection of hydrogen bonding. Also discuss detection of ring strain. Okay, so if the ring strain increase, IR stretching frequency also decrease increase, sorry. Okay, so carbonyl stretching frequency increase with increasing strain and decrease the size of a ring. Okay, so these points also discussed in last lecture. So today we are discuss PMR spectroscopy. So PMR is the proton magnetic resonance spectroscopy. Okay, so in this chapter we discuss a first what is the PMR spectroscopy, proton magnetic resonance spectroscopy, basic principle of proton magnetic resonance spectroscopy, then magnetic nuclei or non-magnetic nuclei, which one is the magnetic and which one is the non-magnetic. Okay, so means it NMR active or non-active. Okay, then nuclear excitation, generation of energy levels. These points discussed in this lecture. Okay, so here first NMR. Okay, NMR is the nuclear magnetic resonance spectroscopy. So there are different types of nuclei involved in this NMR spectroscopy. nuclear magnetic resonance spectroscopy, such as hydrogen, carbon, nitrogen, phosphorus. This is the different types of nuclei are present. Okay, so these different types of nuclei reacts with electromagnetic radiation, such as radio frequency, such as nuclear magnetic resonance spectroscopy. There are different types of nuclei used in nuclear magnetic resonance spectroscopy for the determination of hydrogen, determination of nitrogen, determination of phosphorus, etc. So in this chapter we use as a nuclei such as hydrogen means proton. Okay, so hydrogen nuclei it's proton, so we call a proton magnetic resonance spectroscopy, PMR. Okay, only include in our syllabus proton magnetic resonance spectroscopy. Others are not included in our syllabus. So last few lectures we discuss a introduction of spectroscopy, then IR spectroscopy, UV spectroscopy. Okay, so these three types of spectroscopy we are discussed in last lecture. Okay, so first in UV spectroscopy we discuss a electromagnetic spectrum. Okay, so what is the electromagnetic spectrum? So electromagnetic radiation arrange electromagnetic radiation, different types of radiations arrange in the pattern. Okay, so like this in this figure. So first cosmic rays, then gamma rays, X rays, UV, visible, IR, microwave, radar, TV, radio. Okay, so this is the different radiation arranged in the sequence. Okay, so these arrange in different wavelength. Okay, so cosmic ray has highest energetic and its lowest lambda means wavelength. Okay, so increasing the wavelength, arranging this cosmic ray has highest frequency, highest energetic, so lowest wavelength. Okay, so then gamma rays, decreasing the energy, X-ray, UV, visible, IR, then micro, then radar. Okay, so UV regions occurs in 100 nanometers to 400 nanometers. Okay, but UV in our syllabus we discuss UV radiation. Its range near about 200 to 400 nanometer. Visible range, visible radiation occurs in 400 to 800 nanometers. Okay, so these UV radiation absorb chromophoric group, also discussed in different types of groups, are present in oxochrome, also present in the molecules. Okay, so chromophore absorb these radiation at a 200 to 400 nanometers. Okay, so chromophoric groups absorb electromagnetic radiation and they forms a uh, higher frequency. Okay, so then chromophoric, this is the chromophoric groups, and then we also discuss a oxochrome. Okay, if chromophore are present, the particular frequency are absorbed. Okay, but these chromophore also helps to oxochrome. Okay, so oxochromes are present in the molecules, they enhance the absorption of wavelength. Okay, so there are different types of groups are present, also discuss shift, there are different types of shifts present. Okay, hypochromic shift, hyperchromic shift. So UV radiation, UV spectroscopy we use to determination of conjugation, homoannular diene, heteroannular diene, different types of conjugate we are identify by using UV spectroscopy. So similar we also discuss a IR. So in this IR spectroscopy we discuss a IR radiation, and these IR radiation occurs in 800 to 1005 centimeter inverse. Sorry, here mistake. 800 to 1005 nanometers, its wavelength. Okay, IR regions occurs in electromagnetic spectrum 800 to 1000 centimeter inverse. Okay, so there are different IR regions, near IR regions and far IR regions. Okay, so near IR regions after the visible radiation. Okay, so IR region occurs 800 to 10 raised to 5 centimeter, 10 raised to 5 nanometer. Okay, so this is the IR region after microwave region. So this is the far IR region. Okay, so IR spectroscopy helps to the determination of functional group. Okay, particular functional group absorb a particular IR radiation and they predict in IR frequency. Okay, so this UV spectroscopy helps to the determination of conjugation. Okay, homoannular diene, heteroannular diene, conjugated and non-conjugated double bonds. Okay, so there are different conjugation occurs at different frequency. Okay, so these identify in UV spectroscopy. Similarly, in IR spectroscopy, we identify the functional group. Okay, so these functional group, particular functional group absorbs a particular IR frequency and then occurs a IR region. Okay, so these frequency, suppose aldehyde. Okay, so aldehyde absorb IR radiation at 1720 centimeter inverse, but ketone. Okay, so there are methyl groups, two methyl groups act as a plus I effect. So decrease the frequency of ketone, carbonyl group, because plus I effect. Okay, so these frequency are also affected on function plus I or minus I effect. Similarly, steric, similarly conjugation. Okay, so there are different groups affect the frequency in IR region. Okay, so similarly, radio waves are used in PMR spectroscopy. Means proton magnetic resonance spectroscopy, we use a radio waves. Okay, so these radio waves placed in this electromagnetic spectrum near about, so PMR spectroscopy, proton magnetic spectroscopy, we use a radio waves, and these radio waves occurs in 10 raised to 10 nanometers to 10 raised to 11 nanometers. Okay, in electromagnetic spectrum regions of radio waves, these radio waves use in PMR spectroscopy. So these radio waves, electromagnetic radiation, okay, interacts with matter to form a spectrum. Okay, so these spectrum used to determine the structure. Okay, so if we use a PMR spectroscopy in which radio waves we use to determine the structure of compound, in this structural illustration we use the PMR spectroscopy. So environment of hydrogen, to determine prediction of hydrogen, environment of hydrogen in the molecules, we use a PMR spectroscopy. Okay, so this PMR spectroscopy, first phenomena of proton magnetic resonance, PMR, first observed in 1946. Okay, so thus this useful method for structure illustration or structure determination Okay, so we use molecule absorb UV at a 200 to 400 nanometers. Okay, for determination of conjugation or double bond. If we use IR radiation near about 800 to 10 raised to 5 nanometer inverse region for determination of functional group. So we use radio waves 10 raised to 10 to 10 raised to 11 nanometer to determine the hydrogen, okay, environment of hydrogen in molecules. Okay, so the proton is excited to higher energy level and absorb spectrum, so obtain can be give a lot of valuable information about the structure of molecules. So that's why we use a PMR spectroscopy, proton magnetic resonance spectroscopy. Okay, so next lecture we are discuss basic principle of PMR spectroscopy, nuclear excitation, generation of nuclear energy levels, and precessional motion or gyroscopic motion. Okay, so these points were discussed in next lecture. Okay, so thank you for watching this video. Have a nice day.